Okay, welcome everyone. Today I wanted to tell you about what I'm calling collectives. It's a term for what these guys feel like to me, tensor monoids in poly. So if you remember, poly has as objects things like, I'm going to assume you know what poly is, but it has things like p is like y squared plus 2y plus 1. I should probably draw that bigger. Or one I'll use today is list, which is 1 plus y squared plus dot, dot, dot. And the objects are polynomials. We think of them as polynomial functors sometimes, but you can just draw them as polynomials. And I call these the positions, like there's a position here, there's 2 positions here, and 1 position here. So they're the representables. So this has 4 positions. This has natural number of many positions. And always P of 1 is the set of positions. So if you think about dynamical systems, these would be like positions the machine could be in. And then given any position, there is some exponent there, and that is the directions. So if I had some position here, then P bracket I would denote the directions. Those are kind of like you give the polynomial like, hey, I want you to move left. That's like a direction you're giving it. But also for vector fields, these will be like the vectors. And for categories, these are like the maps out of something. So it always kind of feels like directions. And so the formula is that a polynomial is the sum over all of its positions of y to the directions there. And a tensor monoid is one of these. Oh, and then there's a tensor product. And the tensor product, there's lots of different monoidal products. But with what you do is if P is the sum of those guys, you would just add them up. You'd add those guys up and add the Q ones up. So a position in this thing is a position in I and a position in J. And then the directions there are just the product, a direction in I, a direction of P at I times a direction of Q at J. So this is a tensor product, and the monoidal unit is Y. Because if I only had one position, this only has one position, and so this sum end kind of goes away. And then at that point, I only have one direction, so this factor goes away. And so we have this monoidal category, and you can just ask when you have a monoidal category, what are the comonoids, what are the monoids, stuff like that. And so I want to, the plan for the talk will be, 1, I'll talk about tensor monoids, tensor comonoids, and they're really simple. 2, I'll talk about tensor monoids, and they're the subject of the talk, and I call them collectives. And first of all, I'll define or kind of work through the definition. And then I'll give a bunch of examples. And then if there's time, maybe I'll talk about bimonoids, which are comonoids and monoids that satisfy some property together. Another interesting thing to talk about would be modules over a monoid, but I don't have much to say yet because I haven't gotten very far. But so I'm not going to talk about modules over monoids, but maybe some other time. Okay, so how's the board size for people at home? So look, can you read it? Okay, great, great. Okay, thanks. So tensor comonoids are simple. What's a tensor comonoid? A comonoid would be a C, a map from C to the monoidal unit called epsilon, say, and a map from C to C tensor C called delta. And they would satisfy some properties, like if you go from C to C tensor C, and then back down to C, or up to C, sorry, I didn't give myself much room there, I get the identity. So what does this mean? This is the delta, and this is C tensor epsilon. So just copy this and just throw away that thing kind of. And this one's epsilon tensor C. And that's probably too small for people, but hopefully you might know it. If not, you could find it on Wikipedia or something what a comonoid is. And the other rule would be that C to C tensor C, where you just kind of do this delta thing, and then you go to C tensor C, that this diagram commutes. Whether you copy C and then do delta, or do delta and then copy C, this commutes. So for a tensor comonoid, one thing we can do is we can go from poly to set by taking a polynomial and mapping it to P of 1, the set of positions. And this sends tensor to times. So the tensor product of two polynomials, when you throw away this data, you plug in 1 for y, that's what P of 1 means, then all you see is that this thing goes away. It just becomes 1 to something, so that goes away. And you just get a pair of a position, like what you get a pair of a position in P and a position in Q. So tensor sends, this map sent from polynomials to sets sends tensor to times. And what that means is that if I had a comonoid in poly, then C of 1 will be a comonoid in set. We'll get a map from C to C tensor, from C of 1 to C tensor C of 1. But that's just C of 1 times C of 1. So, and there's a fact called Fox's theorem that says if you had a comonoid in set, and it'll satisfy all the same rules. So C of 1 is a comonoid in set. And so has no structure, and all comonoids in set are trivial in the sense that there's a unique comonoid structure on every set. If you had a set like 1, 2, 3, 4, 5, or the natural numbers, there's only one way to assign a comonoid structure on it. And what it'll be is this will be the diagonal. So if this is a set, it'll just send an element to that element twice. Okay, so this says that on the positions, nothing's happening. And then if you read out what it says for, if you want to read out what the rest of the structure of a comonoid is, it says that if I have a position, then I get a map. It turns out I get a map from Ci times Ci to Ci. I wrote this one first. That'll be delta. I'm kind of assuming you know polynomial maps, which I know not everyone does. But this will be delta sharp I. It'll give me a map from C bracket I, the directions at position I, times the directions at position I to the directions at position I, and it'll give me a special element of that thing. It'll give me a map from 1 to the positions at I. So it'll give me some special element of this set, and it'll give me a way of multiplying two elements to get 1, and these diagrams commute. And so all that means is that C bracket I is a monoid. So the upshot is that a comonoid in poly, a tensor comonoid in poly, is just a collection, just a set of monoids. So it's just like this set of positions, and at every position you have a monoid sitting there. And often it's good to think of polynomial functors as sheaves, and so this would be a sheaf of monoids. So if we weren't working in set, but in another topos, then this would give us sheaves of monoids. So since we're going to work in set today, tensor comonoids are simple. They're just a bunch of monoids. That's all they come out to be. Now, you may know that this sort of comonoid, there's another monoidal structure on poly, given by composition of polynomials, which I often write this way. This kind of comonoid are categories. Exactly categories. That's a weird fact. And so you might say, it turns out that this kind of comonoid is this kind of comonoid because if I had a collection of monoids, if I had a whole bunch of monoids, I could consider that as a category, which is like as many objects as there are positions, and each one of them has just loops to itself. So it's kind of a weird category, but it does give you one. I'll just erase that. Okay, but the point was that this is not that interesting. So tensor comonoids are simple and not that interesting. Yeah, David?
So if I think about a poly as an interface interface was a comonoid, a tensor comonoid, then I would have a codiagonal. And wiring that together, wiring a system together with that would give me my new interface would be C tensor C. And so is it correct to say that what's happening here is that in the bottom, it would just duplicate out my outputs. But for my inputs, I would take them and multiply them and then push them in.
That's right. So David asked, from the perspective of dynamical systems, how should you think of this? And it's kind of weird because when we think of dynamical systems, we usually wire several together to make one. But here we're seeming to wire one together to kind of make several somehow. So, but the point is, what David was saying was that if I had a position of the internal thing, it would give me kind of two positions to work with. It would copy it. And then if I got feedback or input on those two positions, I would have a way using the monoid structure to add them and give it something for the other one to do, for the one to do. So I guess it would kind of like, yeah, I don't know. Yeah, I don't know. Yeah, so yes, that's what it would do. But it's much more, yeah. Well, it's much more interesting, I think, from the at least wiring diagram point of view, to imagine tensor monoids, which I'm going to call collectives. And tensor monoids, if M was a tensor monoid, we'd have this map from Y to M called eta, and a map from M tensor M to M called mu. And what it would let us do is it would let us, if M was it would let us like kind of have many M's together, and it would be a formula that we always had for taking M's inside and getting an M outside. So we have a bunch of little machines, each with interface M. We don't know what, M is some polynomial that we're going to assign a monoid structure to. So each has the same interface. And if I had like 4 of them or 3 of them together, I could put the same interface around them, and they would all be able to contribute their, their positions and make one position for the outer box. And then when that outer box got some feedback or some input, it would distribute that input to the 3 inside in such a way that if inside this little one was even more small ones, then it'd be kind of frictionless in the sense that like this guy could then distribute it to their internal things. And it was as though we didn't have to write this intermediary box. It's frictionless. So if there was some kind of very, very, very low level one of these, if at the lowest level there is actual dynamical systems running these guys, then M would be a kind of universal router or something, where like all these different things would be contributing their positions to this and to this and to this, and then they would be aggregated or contributed to a position of this whole thing. And then if we gave a direction there or some feedback, that would be distributed to these 3, and then those would be distributed again. And so the little tiny dynamical systems at the bottom would just like get a little input and do their thing with it. And we know it doesn't depend on how we grouped them. That's what that does. But let me say, so I think this is the more like, from a wiring diagram point of view, this one's more interesting, or it fits that formula or formalism better. But it also is really a weird and interesting structure. So let me say what it is. First of all, if we apply 1, we get a monoid. So if we get a map from 1 to M of 1, 1 is the one element set, and I'll call this map E. So E is eta of 1. And we get a map from M times, M of 1, the positions, times M of 1 to M of 1. And I'll call this thing star. So that'll be, so M of 1 with E and star is a monoid in set, a regular old monoid. You could ask this thing to be commutative or not, but it's a monoid in set like the natural numbers or the integers or any group. So what are the rules here, by the way? It's that if you go from M to M tensor M and then back down to M, so first you, wrong button. M to M tensor M, like that. So okay. First you do M tensor eta, or you do eta tensor M. That gives you a way to go from like m tensor y. So m tensor y, by the way, is m. Okay, so it gives you a way to go in, and then you can multiply. And these should commute, those two diagrams should commute. And the other one says that m tensor m going to m tensor m in one of two ways, and then completed to m. So if I multiply, that commutes too. Okay, so what we find though is that the positions of m must be a monoid. So we know how to combine positions. So I think of these positions of m as contributions. So each of them is contributing something. Each of these little dynamical systems is contributing its position. And then we're taking all those contributions and we're getting a total contribution of the whole thing. But what we also have is that for any ij in M of 1, if we have two different contributions, we get a map from mi times j. So we multiply them in the monoid, and we get a map from that to m of I times m of j. So we can also take a distribution. If someone wants to disperse something, they hand it to this thing. They say, oh, you guys gave me this contribution and this contribution and all these different contributions. I've added them up. Now the world gives you some feedback, which is some direction here at that total contribution. And your job is to disperse them to a contribution for the first one and a contribution for the second one and so on. So I think of this as like contributions, and they go with, so con is with, I guess, and this is distributions. You distribute it out.
Sorry, where is this map going?
This thing is, so star is mu of 1. And this thing is mu upper sharp ij. It's the thing that takes, so you have an ij position, you multiply them to get a position, you get a feed, you get an input there, and you distribute it back. Okay, but the weird thing is, we said what on positions is going on, but on directions, what do these satisfy, this distribution law? Like, what is it? And also, it's really annoying, or at first it was very annoying to like keep track of like the two factors of this thing. Because this distribution thing gives us two factors. So I want to give you notation, or show you the notation that I use. So what I would write is, I'll write this map, mu sharp ij. It'll be a pair of two things. And I'm about to write notation here, so notation. And the notation is going to be I over I star j, comma j over I star j. But that's slightly ambiguous because this star is the name of our product, whereas this is just plain notation. So if I'm going to put a tiny dot under that star so that you know it's notation, but it really wants to be the star. And you'll see when I write the axioms that it's trying to be the star itself, but it doesn't, it's just a map, so it doesn't know about it. Okay, so what are the rules? The rules are the things that come from these two diagrams. And they say that distributions have to act as follows. I over E star I, E is the monoidal unit, but E star I, this thing is going to be a map from M of E star I to M of I. And this has to be the identity. E star I is I. And similarly, the other one is also identity, I over I star E. So it's like if I multiply I by E, and I get I over I, kind of, I over I is 1. That's why it's the identity. That's supposed to be good. Like it's just good evidence for the notation being intuitive. And the other rule is that, well, there's 3 more that come from this thing. I get 3 rules here. And they say that if I go from I star j star, I star j over I star j star k, and then I do I over I star j, you get I over I star j star k. So let me put some dots. I'll put those weird little dots. So there's little green dots here, and there's a little green dot there, there, there. So these are the real stars, and these are the dotted stars. But the point is, like, a cancellation law is happening. I'm canceling a real star with like this kind of dotted star, but the dotted star is trying to just be star. So it's just a cancellation law is what you're supposed to see there. So these are maps from M bracket I star j star k to M of I. So that's the first rule coming from this thing. The second one, they're all kind of the same. So if I take I star j, so I distribute, what is this talking about? This is talking about if I had three things, three m's, and I either wanted to group them like this or like this. How should I distribute? And the point is that it should distribute the same either way. So this one says, if I first group them like this, and I sent some distribution there and some distribution there, and then inside of here I distribute it again, it would be the same as taking the whole thing and distributing to just the I one. So that worked out. I star j star k, composed with j I star j, should be j star k over I star j star k, composed j over j star k. So again, you're just canceling. If I cancel either way, here I'm canceling that, here I'm canceling that. And then in the third one, it's the same thing again. J star k over I star j star k, composed with k over I star, over j star k, is k over I star j star k. Okay, so those are some weird rules. They're just the rules you get from here using this notation. So this notation is useful, I think, to make calculations here. But I think it's also nice because it's going to give us like some intuition when we think about examples. And that is the next part of the talk, is a bunch of different examples. Okay, so any questions?
Yeah, I was going to ask if you've come up with a way of drawing the distribution yet. Is it like splitting wires? Or?
I don't have a way of drawing it. Yeah, this is the closest, this notation. Yeah.
So just to summarize the rules, if you draw them as fractions, if you draw the distribution of something in I star j as I over I star j, j over I star j, and then you multiply them out as if they were fractions, those are the rules that you get, but where multiplication for the top things is composition of functions.
Yes, so David asked on Zoom, if I take the distribution rules that come from these monoid rules, and I write the thing that goes from the directions at I star j to the directions of I and the directions of j as though they were fractions, then the rules become fraction cancellation, where I'm not canceling the star as though it was, the star is not interacting with this division sign as much as you might think. That's why I chose star rather than asterisk, because this star could be plus, it could be times, it could be any monoidal, it could be any monoid law. So the star is not interacting with the division. All that I'm canceling is across two different, the division is kind of like from function composition, yeah. Right, so let me give examples and hopefully it'll become clearer. So one, for any set S, y to the S has a unique, I guess we always start with boring collective structure or tensor monoid structure. So this is a collective, and the reason is because it only has one contribution it can make, one position it can be in, and so all of them are in this contribution. Everyone just gives their unique thing. They all say yay or whatever, and then yay comes outside, and then an element of S is given as feedback, and it's just distributed to everyone diagonally. Everyone just receives the exact same thing. So that's boring. 2, for any monoid, M-E star, M-Y has a collective, is a collective. And that's pretty similar. It's just saying that if you knew how to aggregate people's, all these different things as contributions, and then at the end, the outside world just says yay or whatever, and you just or keep going, that's what it kind of says, keep going, then you just distribute to everyone, keep going. And then they just all update their internal state. So those are boring. But another one is that there's an adjunction. This is more like a proposition, I guess. There's an adjunction. So I'll say prop, I guess. Well, whatever. Adjunction from poly to collectives. Collectives is the name I'm giving this thing, equals tensor monoids. And so every collective, every tensor monoid has an underlying polynomial, M. But this thing is like the free collective. So free of some polynomial is y plus p tensor p plus p tensor p tensor p. And that is a tensor monoid. Let me just say a few, So what is this thing? This is saying if you had any polynomial, so you have any interface you want, then you could have M be that a contribution you can make is either one element of P, one output of P, or no outputs of P, or sorry, none, 1, 2, 3, like some number of positions. So this thing's just like manufacturing like 12, it manufactured 12 positions today, and another one manufactured 18 positions today. And so when you put them together, you've manufactured 30 positions of P today. And then the outside world gives you 30 directions, and you give them back, the first 12 to the first guy and the second 18 to the second guy. So it's kind of just like, it is an organization, like, it's keeping track of all the stuff for you, but it isn't doing much very interesting. But it's still, I don't know, it's kind of interesting. And by the way, U preserves, by the way, collectives has limits, so it has all limits, and then it also has, times is a limit, but it also has tensor and these 3 monoidal products. And U preserves times, U preserves limits, I won't put that one, limits, tensor, and composition. And what that means is if you had 2 polynomial monoids, if you had 2 collectives, you could compose their P's, their polynomials, you could tensor their P's, you could multiply their P's, you could take a limit of their P's, and you would get another, there would be a unique way to put a collective, there would be a given monoidal way to put a collective structure on that. So you can just look at the underlying polynomials and do limits and tensor and to them, and then put back the collective structure. So that's already a bunch of them, a bunch of different ones, but none of them are very interesting yet. So let's go to the actually interesting ones. So here's the one where the notation came from. So I'm going to use M is the reals greater than 0, y to the reals. And so this is saying that a position or output or contribution you can make is a real number that's bigger than or equal to 0. And then I'm going to give you a direction, which is some real number. And so what we do is on the underlying monoid, on the underlying sets, I'm just going to use plus. So a bunch of things all contribute a number, and we add them together. And the monoidal unit is 0. But how do we go back? So what is I over I plus j? If I and j are positive, non-negative real numbers, I over I plus j of D. So D is just some real, is I over I plus j of D times D. So I guess that one's like dotted. And that one's actual real number addition. And j over I plus j of D is j over I plus j D. So it's kind of saying the first one says contributes 5 and the second one contributes 10. And then we give it a reward of 1. Then it would give 1/3 to the first one and 2/3 to the second one. It just like, they just add up. I don't know how to draw it. They just add up and then you just send back you just distribute, oh, you contributed 1/3 to our total, you contributed 2/3 to our total. So here's my total feedback or like return on the investment or whatever. And distribute it among you accordingly. And so that's what this collective does. That's a kind of, I think it's kind of a neat one.
Investing in stock.
Yeah, it's like investing in stock. Like this one invests I dollars and this one invests j dollars, and then we get some return and we give I over I plus j to the first person, j over I plus j to the second person. Okay, so that's an example. There's 2 examples with list. So let's do m equals list. And list, if you remember, is 1 plus y squared plus dot, dot, dot. Okay, so in the first one, I'm going to give, this one is commutative. I'm going to give you another commutative one. And so it goes from the positions of this are the natural numbers. And so I need a monoid structure on the natural numbers. And there are 2 that I can think of right now. And this one is going to send 1, the middle unit will be 1, and the monoidal product will be times. Okay, so what does it do on directions? What is I over I? Maybe I'll write times here. I don't know if that's illegal, but I over I times j is going to be a map from, so let me write this again. Let me rewrite list as sum over I in the naturals of y to the 0, 1, dot, 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 I minus 1. Okay, then I over I times j will go from 0 through I times j to 0 through I. Does anyone have an idea what this could be? Yes, Owen?
You're going to be like mod j or?
Yeah, close. This is div j, which looks just like the notation again. So you take a number from 0 to I times j minus 1 and divide it by j, throw away the remainder, and that'll give you, all this is doing is it's taking I times j, I by j, picking a dot in it and projecting it down to the ith and to the jth coordinates. So what it's doing is it's taking I times j and remembering, since it's a polynomial, it knows where the I times j comes from. It knows it's 3 times 5 and not 15 times 1. And so it knows how to distribute a number between 1 and 14, 0 and 14 to 3 and 5 and not to 15 and 1. And of course, j over I times j is div I. Yes?
Is there a way of like rejiggering this so that it does like one of them is divided by I and the other one is like modified I?
So the question was whether there's a way of having one be div I and the other one be mod I, and I don't. Are they different?
Well, it depends on exactly how you write it, but if you draw like.
Okay, maybe I should be a little more careful. All I really should be saying here is that this is the 2 projections, like that I times j, like the number.
So you're thinking of I times j as the set of tuples.
I'm thinking of I times j as isomorphic to the set of tuples, and then I'm just projecting onto the 2 things.
So if you write it as 0 to I times j minus 1, then 1 is div I and one is mod I.
Yeah, it should be, yeah. So I hope I'm right, but this is what I'm really doing in case I made a calculation error. Okay, so let me do another example of list. So again, I'll have M be list, but the map from the naturals times the naturals to the naturals will be plus instead. And so what I need to tell you is what I over I plus j should be as a map from 0 through, well, I'd prefer, if it's okay, to think of list this time as the sum of I in the naturals of y to the 1 through I. It doesn't make much difference, it just makes the formula a tiny bit prettier. So what I need is a map from 1 through I plus j to 1 through I. And I need another one, j from 1 to I plus j. So what does this collective do? This is a way that some people can hang out together and contribute some stuff. So each of them says a number. One of them says, oh, I contributed 3 widgets. And the other one says, I contributed 10 widgets. But in this collective, which is non-commutative, the first one gets paid first. So when D comes in, if D is here, I over I plus j. So here's one where the notation doesn't quite work unless you think of it a little more abstractly. It says if I plus j comes in, sorry, if D comes in, what I'll do is take the min of 0, the max of D and I. No, the min of D and I, sorry, one last time, the min of D and I. So if D is less than I pay the first guy D dollars. If D is bigger than I pay the first guy I dollars, his or her full investment. Whereas J over I plus J of D is the max of 0 and D minus I. So if D is here and D minus I is negative, well, we pay this guy $0. And if D is up here, then we pay this guy I dollars, and we pay this guy D minus I dollars. So it's kind of just like where we pay this guy after the first one gets paid. We pay the rest to that guy. And I don't know if there is another monoid structure on list, but I think it's a pretty interesting thing that like this, it feels like a well, I guess that's the reason for the name, is it feels kind of like a collective, like some people have gotten together and made a rule for like contributing to something. And then when a distribution is given, they have a rule for giving it back such that it's kind of frictionless or associative, and you can spread it out. I don't know if I had any more examples.
Did you say you get a monoid structure on list too many monoid structure on natural numbers?
You would get a monoid structure on naturals times y from this one. But you wouldn't necessarily get, which means that when the only feedback or input you can get is keep going, you can tell everyone in your room to keep going. But I don't know if there is, for every monoid structure on the naturals, there is a tensor monoid or collective structure on list. I don't know that.
So what? Okay.
This one was.
I don't understand all of that stuff you just said, but right at that stage, you said, I only know 2 now.
Oh, I only know.
Yeah.
Yeah. So John was asking if at this stage, number 5.
If someone told you a whole.
If someone told me a new monoid structure on list. In fact, I think there's one where you take I plus j plus I times j is a monoid structure on the naturals. But I don't know if it extends to a monoid structure on list as a polynomial.
So why do those depend on j?
Oh, I have great other examples. Sorry. Okay.
Could
Why doesn't this depend on j? Well, D is a number between 0 and I plus j.
Okay.
Right. So given any number between between 0 and I plus j, if it's, yeah, what I'll do is I'll pay I first. But yeah, it doesn't really depend on J.
Why is
Is
it
it
one?
just shows-
Was there a 1?
Like, I don't know.
Where's a 1?
Right above 0, it says 1.
Yeah. it
Here?
could be either-
Ah,
Well, no, that
that should be one, that should be one.
It should be
Oh.
18, one of them.
yes, okay.
Always get paid one.
Sorry, guy. Okay, I guess I should go to 0 and I go,
No,
yeah.
no.
No? 1. Okay.
Your best way.
No,
Okay.
that's what is wrong.
Change indices as you like.
Okay.
But now, max of 0, can Jay, the second guy, get paid 0?
No, no. So I messed up.
Just add a +1.
Yeah.
Always paid?
Ay. Sorry.
You always get 1 point.
Yeah, so there's a slight mistake here, but it's not, hopefully not terrible. I think it's, 0, 1, -1, +1. But I still think it's right that, I still hope it's right that this is correct. Maybe what I did originally was I used, I don't know what I did.
So for any monoid structure you can put on positions, there's lots of structures you can put on the directions, but there has to be a certain compatibility.
Yeah, the question was, given a monoid structure on the positions, there may be many monoid structures on the whole polynomial, but they have to satisfy conditions. Yeah. So sorry about this error here. I guess homework is to figure it out, and I will do the same. So let me give another source of examples. 7. This thing, monoid, has an underlying collective structure. And so what that means is, for example, any operad with one object is a tensor monoid, and therefore has a tensor monoid structure also. So that's a set of examples, but I don't think those are, for some reason, they're not that enlightening for me. So I'm going to skip them unless I have extra time at the end and I can tell you about them, but just prepare to be like, why is that good? So it's not, somehow for me, I don't get why this is interesting yet as a collective, or but we could go through it. But sorry, no, number 7 is very interesting, but the one about operads. So any operad with one object is this thing monoid and hence a collective, but not very interesting. But I can't see why to care right now.
I'm confused because you said that those arrow monoids were categories.
Oh, arrow comonoids are categories. Yep. Yeah, composition comonoids are categories. Polynomial comonads are categories. Operads are tensor monoids, but they're not the only ones. Yeah, David?
Is it too difficult to say what if you took the operad of probabilities?
Okay, I guess there's some popular demand to say what it is. I don't know exactly, but here's what you do. What you would do is if O is an operad, then O of n is the set of operations of arity n. And so what I could do is write sum over operations of all arities of y to the arity. And this thing will be a tensor monoid. And so what is it saying? It's saying that if we're thinking of these as collectives, everyone is contributing an operation. So Alice contributes an operation and Bob contributes an operation. And the way we combine them is, if Alice was first, we just write, we kind of do this thing. Alice, Bob, Bob, Bob.
What do
Well, because tensor monoids are not necessarily commutative, so I'm allowed to do that. And this is what we're going to do. We're going to take all of the different operads. So we had 3 things. Each one's contributing some stuff. We would put the first operation, then the second operations as many times as required, and then the third operations. And then, as a direction, someone comes in and points to one of these 6. And then we tell B which one they pointed to, and we tell A which one they pointed to. And I don't see the point of that. But I guess for probabilities, what would it be? So you say, I have n many things that could happen, and I have them adding up to 1. Yeah, so I guess A rolls a dice, and then B flips a coin no matter what we get. And then we say whether we got heads or tails. We say which one we got, and then both of them know. Oh, that's a really good one. Thanks, David. So we tell them what the outcome was. So if this one was, these operations are, for probability operad, we would get like, 1/2, 1/4, 1/4, and then this one might be 2/3, 1/3, and then this says we get some distribution of like 6th here or something, and then we tell them both what happened. Like someone actually flips the coin and we tell them all what happened. Okay, so that's great. That's a collective of a bunch of gamblers or whatever.
When you say,
I had been thinking about like May's like little cube operad, and like somehow just putting the same one in all of them, and then like someone picks a box, and I just didn't know the point. But this is much nicer, so thanks. Yeah.
do you mean a general monoidal operad or Cartesian?
I mean an operad in the sense of I think May, but I think but I'm not sure. So I think a plain operad with one object. Okay, so you have n-area operations and you can compose them. But when we do this sort of monoid, we'd actually get to compose them no matter, like, you could compose them with different ones here. But with this tensory sort of monoid, thank you, David Jazz, saves the day, okay. With this sort of monoid, you have to plug in the same one to all the interior boxes. Okay, so the last example I want to give is for any category. So think in your mind of any category you want. C, this thing, I in ob C, y to the C bracket I, where C bracket I is the coproduct of all j in ob C of hom ij. So here's a polynomial, and the polynomial has positions, the objects of C, and at any position, the directions there are the outgoing maps. And that thing is a comonoid. And in fact, every comonoid in poly is a category. But what's interesting is that I'll call this thing C. C, this is a different brackety symbol. This is the internal hom. This thing is a collective. And so I wanted to tell you what that looks like. So C bracket Y as a polynomial is the sum over all phi taking C to Y of Y to the C of 1. But this, now I have to tell you what that is. That's a polynomial map. So what this says is a position of C bracket CY is a map from C to Y. So I want to tell you what that means. And then a direction is just a choice of object in C. So what is a map from C to Y? If C is your category, so you have this category, it's got objects, it's got arrows, it's any category you want. And now a map from C to Y is for every object in C, pick one arrow. Any arrow you want. That one had an identity arrow on it. So every object gets an arrow. So it's a direction field on the category. So as an example of a category, you might think of C is, let's see, how do I write this? Rn, y to the tangent space of Rn, tangent bundle, tangents, sum over x in Rn of the tangent space at x of Rn. And this is a category, so it would take Rn, and it would say at every point, what are my directions? My direction is a tangent space there. And that's a category because I can take that tangent vector and the current point and just add them, because it's a trivial tangent bundle. So I can actually add them, and that will give me a new point in Rn. And now a map from C to Y would, for every point in Rn, pick an element of the tangent space there. Now it won't be continuous, so that's kind of bad. It's just picking like arbitrary arrows. But if I worked in a Topos besides set where I could encode continuity, then this would be continuous. So it's not bad. You just have to decide if you care. And if you care, you have to work in a Topos that cares. But anyway, it would actually pick a vector bundle of your, sorry, a vector field on Rn. Okay, so the point is, did you have a question, Owen? You can do it. So, okay, let's take any space. Then I would use the space of all little x and big X of y to the sum over d in R plus. So I'm going to take as my positions the points in X, and as a direction, pick a length, and then give me a map from 0d, the interval, to X. So give me a, so that'll say we have this space X, any topological space you want, the positions are the points, and the maps are length d curves parameterized by something of length d. And the codomain will be where it lands, and the composition will be composition of paths. Yeah, so you can do that, and that's a category. Now, what would C bracket Y be for this? It would be for every point in the space, picking a path out of it of some length. And again, if you use a Topos that likes continuity or cares about continuity, then this will be continuous in the point. Okay, so why do I care about this? It's because C bracket Y always has a tensor monoid structure. So C bracket, that was supposed to be C bracket Y has a tensor monoid or collective structure.
Sorry.
Sure. Question?
I was just wondering, how does that formula correspond to a direction field? So
This one?
No, just the plain old general thing for a category. So P from C to Y is equivalent to the choice of an object.
So the question was, how is the position of a bracket CY, the internal HOM, how is the position of it something like a direction field? And the answer is that it is for every object in C, a choice of outgoing arrow in C. So it's like one of this red thing is a map from C to Y.
And that's equivalent to a morphism from C to Y, is for every object in C.
Yes, a morphism. So poly CY is the product over I in ob C, or C is any polynomial here, of C bracket I. Yeah. Okay, so this collective, the positions, or what things are contributing, are vector fields. So this thing is contributing vector fields. And we have a bunch of different things. Each of them are contributing vector fields. And then somebody comes in and says, now distribute this point. So they point at a point in the manifold or whatever, and they say distribute it. And so our job is to understand how we're going to take a bunch of vector fields and make a vector field, and then how we're going to take a choice of object or point in the space and distribute it to a bunch of points in the space. And so the answer is, well, maybe you can guess. So if you had two vector fields on the category, in other words, for every object you assign an arrow going out. And then somebody else, for every object, they assign an arrow going out. And your job is to somehow aggregate them. Does anyone have an idea of how you would get for every object an arrow going out? Compose, yep. So if I had gamma, some kind of global section or something. So we have for every object an arrow going out. And another one, gamma 2 in C bracket y of 1, which is product over I in C of 1 of C bracket I. So if we had these two things, then I'd take gamma 1, I'd take its codomain. Since we're in a category, we can take codomains. And then I'd take gamma 2 there.
But, oh.
So that's how I would combine contributions. If everyone's contributing a vector field, I will combine them by just running one after the other after the other. And
You do something else, like average the vector fields, like maybe like in a metric space, say, rather than arbitrary collection. Like,
so Tim asks, could you instead average the vector fields if you were in some kind of metric space or you had the structure? I don't know. So this example is only for categories where we don't have that structure. And so it may be that there's another cool collective or tensor monoid where you use a different kind of structure. But yeah, not for this. But right, so what we have now is we have the ability to take different vector fields and multiply them together or compose them. And now we need that if somebody gave us, after we took, everyone in this room, everyone can combine, takes a vector field, picks a vector field on the category, and we run one after the other in order. And then somebody out there points to a dot somewhere in the category. And our job is to distribute to everyone a dot. Everyone's supposed to get a dot. What should we do? So someone gives us someone comes in and points to a, oh, I see. So now let's pick another one. So let's pick a green vector field. Okay, well, I guess there was one of these all along, actually. And this one, and this one.
Just take each person's arrow out.
Okay, so one suggestion was, we have this dot, somebody gives it to us. We've combined all the vector fields. So we ran red and then green. So at this point, we went to this one. At this point, we went to that one. At this point, we went red and then green. And at this point, we went red and then green. And now someone points to a dot. And one suggestion would be, well, take the red's codomain and the green's codomain. And that is not it. So other suggestions? At least I don't think, that's not the one that comes to us from this formula, using the fact that this is a comonoid directly. So the one that comes to us from this formula, someone has an idea.
I know.
Oh, someone who knows has an idea. Okay, the answer is if someone points to one of these, then we need to distribute it. What we do is we give the red person that dot, and we give the green person that dot, like whatever red said to do. So in other words, if we had all of us doing this, we each contribute a vector field, then someone points to a dot, then first it'll say that dot, then it'll hand to the next person the codomain, then to the next person. So it'll just like run all those vector fields and show you the dots of like where they landed along the way. So it just kind of plots the thing you would write on the Julia screen or something. It would just like plot the order. Like if you had the same vector field done 10 times, it would just plot where that dot went after the 10 times.
It's kind of like you give the first person a cake, they take a bite of the cake, they pass it to the second person, they take a bite.
Yeah.
What if the graph is disconnected? Like there's someone who's not connected to the point that got picked?
Every person has picked a vector field on the entire category. So there's no way that a disconnected category could cause a problem. So I thought that was neat because it just seems to print out like the results of running these different vector fields in order. So I think my time is up. So thank you.